2, 1. So second derivative, and now moving into concave up and concave down. And then sometimes, the utilization of these concave up and concave down is pretty useful. In particular, if we're trying to find kind of local maximums, local minimums, and sometimes even absolute maximums and absolute minimums. So talking about those kind of critical points where those happen. I'll put up a link up above there if maybe you have forgotten about that. Now, I will also mention the inflection points. And so these are actual points where things are changing from concave up to concave down, or from concave down to concave up. So you'll see when that particular item happens. Now, the ultimate goal is to try to explain this, and the second derivative, once you take the second derivative, you can tell quite a bit from that with regards to how the function is actually behaving. So visually, what happens. So let me just give you a visual of this concave up and concave down. So for instance, for concave up, so if you have a function and it's starting to change and it almost looks like it's kind of accelerating kind of in this way, and you take any point, okay, on that particular function. If we take a tangent line to that point, so in this case it would be this, you will notice that concave up means that your actual tangent line is going to be below your actual function. Now, of course, aside from the fact that it's touching, okay, at that one particular point. So if you have a function, so at this particular point, so let's call this point A, and then the function is f at A. So at that point, you would take, okay, and you would have your slope, okay, so you would take the first derivative, and then you can find the tangent line to that particular point that is touching it. But what we mean by concave up is that the tangent line lies below the actual function. So it looks like it's concaving upwards, all right? So that's the idea behind this concave up. And now we could have moved this tangent line pretty much anywhere in, at least on what I have drawn. So we could have put it over here, we could have put it over here, it doesn't matter. It always, at that particular point, the function, okay, it would be below the actual function. Now, when you're looking at this, then you might say, well, if you have, let's say if you have functions that are kind of looking like this, and now you really push yourself over here, okay, and then the tangent line looks like that, then you say, like, what do you mean it's below it, right? So here, it looks like, your tangent line is kind of going almost upwards, right? So what do we mean that it is actually below? So in this case, you would say, well, it kind of looks like it's to the left, right? The points are to the actual left. And what I would want you to visualize is anytime we have something like this, all right, you would attach it, and then you can always kind of visualize in your mind that below means that if you would rotate this, okay, and you're rotating it kind of clockwise, so you're going in this direction. So if I'm going to go in this particular direction, you will notice that indeed the tangent line is below, right? Now, if you rotate counterclockwise, okay, then it's going to look like it's above. So that is going to be something to do with concave up. So we are always rotating this clockwise. So in your mind, you can visualize it in that sense. So that is concave up. Now, concave down, well, you can probably decipher that. That means that if your function is moving along, kind of like this, and now again, you try to find a point in here, so any point, and then you're going to be touching, okay, and you're going to be creating a tangent line, then now, all of a sudden, your tangent line is above, and your function is now below. Okay, so that's what actually happens. And again, so now in this sense, like if you have a function which, once again, it kind of looks maybe something, it's kind of like steep like this. And then, you're finding a point all the way over here. Okay, so within that, and then if you attach this line, I'm going to just attach it within here. So now, what do we mean that the function is below it and then the tangent line is above it? So once again, you can, visualize for yourself, always clockwise. Okay, so if you would turn this clockwise, okay, notice that indeed your tangent line would be above and then your function is below. So that means concave down. And it kind of makes sense, right? It's pointing downwards. So this is downwards, and then this function, okay, is kind of pointing you upwards. So this is concave up, and this just is concave down. Now, where this was actually pretty useful, so if you remember, if you were finding local maximum and minimums, so within here, so if we had, okay, something like this, we knew that the tangent line here would have been flat, like so. So if you do that, now you actually have a test to check if it is a local maximum or possibly a local minimum. So within here, so this is what we would have. So right there, okay, and you would have a flat line. So we know that at this point, okay, the actual, so within there is 0. So the derivative, the first derivative is 0, okay, for these. So these are equal to 0 here. And then we always had a problem of like, then we kind of have to find the derivative to the left and to the right and then see if it's a local maximum or minimum. Well, now you have a pure test for it, where you can now take the second derivative. So you can take the second derivative of the function. And if you notice that it is concave down, then it is a local maximum. So now, concave down, what does that mean with respect to your second derivatives? So here it is. If you take your second derivative at that particular point, and, okay, it is less than 0, so this means that it is concave down. So when it's negative, it's concave down. This is concave down. And if you have your second derivative, which is greater than 0, then this means it is concave up. So if it's concave up at a point, so notice right here, it's concave up, the tangent is below, the function is above, so that means that would be a local minimum. So that is a very nice test for us to be able to see these local maximum and minimums, but this idea of concave down and concave up just can be seen through this visualization of the second derivative. Is it positive or is it negative? And now that brings us to the question of, well, what happens if you take the second derivative and it's equal to 0? All right? So what happens in that case? If you take your second derivative and then you're like, well, I got 0. So what does that mean? So you're, walking along and then you're trying to find this and it's 0. So what does that mean? It's neither concave up or concave down? Possibly, okay? And so within here, it's kind of inconclusive. We do need a little bit more information to be able to tell. All right, so I am going to do this and illustrate it to you through an example so that you can see what actually happens. We're going to be using concave up and concave down to see where the functions are, concave up and concave down, and then we're going to run into this problem, and then I'll show you, okay, what happens. So in essence, okay, I'll do it through an example, but what this would mean, so imagine you have a function and this is your point A, all right? And at that particular point, so wherever that might be, so somewhere along here, Okay, so you have your function and you take your second derivative and then you notice that it's 0. So what you're going to have to check is around the vicinity of that particular point, you want to see what happens to the function. Okay, and in that essence, so if you are looking to the left of A, so we know that we have our second derivative here is equal to 0 at A. Now to the left, so our second derivative of our function, if it is, let's say, so if it's negative, which means it's concave down, and to the right, so on the other side, if your derivative is, for instance, greater than 0, so it goes from negative to 0 to positive, so it switches. We call that an inflection point. So it's an inflection point because the function changes from concave down to concave up. Okay? Now, it can also happen in reverse, where the function can change from concave up to concave down. And that also is an inflection point. Now, what do these inflection points mean visually, if you would be visualizing? Because we can visualize, for example, local and maximums and local minimums. You know, it's basically flat derivative. You know, there's some kind of a maximum point there. We can do that. What about these inflection points? What do they mean? What these mean is the following, that the function is moving along, okay, in this case, and then it just switches back. So notice that this is not a local maximum or a minimum in here. We might get a 0 derivative, and notice that here, so if you would take your second derivative, okay, on this range, notice, so anywhere in here, if we put a tangent line, so this looks like it's concave down, and then it hits this point, which would have been our second derivative, okay, let's say this is A, okay, this would have been 0, but then notice what happens, it switches over here, and it's concave up. So this is concave from down to up. So that is an inflection point of a change of your second derivative. So that's one thing that can happen. Now, if the opposite happens, if it goes from concave up and then to concave down, then in this situation, let me put in an extra sheet here. So if you have that happening, then this is what you would visualize. So it's concave up, so that means it's curling up in this way, okay? And then it starts to go concave down in this way. So notice you have an inflection point right here. But this particular point, so this right here, so if you're thinking about your first derivative, so that's interesting. So what would that actually mean, okay, as it's switching, as it's going here? So this is concave up, okay, on this path. Then it looks like it hits this point. This would have been basically your second derivative is equal to some kind of 0. And then it continues on in here, but now it's concave down. So this is concave down. So now you again have an inflection point. This is called an inflection point, but now it's an inflection point from up to down. And here it was from down to up. And I'm going to illustrate that through an example so that you can also see that visually for yourself, okay, to be able to see, okay, what is actually happening here, okay, with respect to possibly derivatives and how does this function look like. So I'll give you an example of this as well. So that's what we have with regards to these inflection points, and they happen whenever your derivative at a particular value is your second derivative is equal to 0. Now, you might ask, well, what else can happen? Is it always from concave up to concave down and from concave down to concave up? Not always. So you have to be careful with this. Don't think that whenever your second derivative is 0, it's always an inflection point. That is not true. It's not always an inflection point. And in fact, so here's an example. If our function was equal to, let's say, x to the 4th. Now, you may remember what the parent function for x to the 4th looks like. So if you graph this out, so let's say if I'm going in this direction, what this would look like, this would be kind of like this, kind of almost like a quadratic, except it's much more kind of, steeper loses is in here. You still have a derivative of equal to 0 here, but notice what happens. If I take my first derivative right here, then what this will be, this is going to be 4x third to the 3. Now, we know, indeed, so that means that we have, at 0, we have a slope of 0. So we have a tangent line, which is 0. But notice what happens. If I take the second derivative of this, which is going to be 12x squared, still this, the second derivative at 0, is still equal to 0. And now you might think, well, is this an inflection point? It's only an inflection point if the function changes from concave up to concave down, or from concave down to concave up. That's an inflection point. It means it's a change in concavity. Okay, I don't even know if I said that correctly. Okay, so if it's concave, okay, if it's that concave concept changes from up to down or from down to up, that's called an inflection point. Here, you can clearly see, so if you go along here, okay, this is concave up. And this, going from here to here, is also concave up. And you can see that because this is our function, and indeed, this function right here, that what we have for this function, this is always greater than 0 for x is not equal to 0. Because no matter what you substitute in there, right, when it's negative, you're going to square it, so it becomes positive, and you're going to multiply by 12. So it's positive, which means it's concave up. And then if you take positive values, the same thing happens. So here, you're going from concave up to concave up, so this is not an inflection point. In fact, this is actually your absolute minimum. So that's another way to be able to see an absolute minimum, or local minimums for that matter, or local maximums. So be careful, okay, so how these things are. So when it's concave up or concave down, and then when you have this 0, it's inconclusive. You still have to be able to check what's happening on the left and on the right of that particular point to conclude if it's an inflection point or if it's a local maximum or local minimum. All right, so be careful with that. Let's look at some actual examples to test this whole thing out. All right, so here is your function. So let's say this is a polynomial. And by the way, when you're studying this, you probably at first will do this with polynomials. If you're going to look at functions which are rational functions or even more complicated, it's actually difficult, right? Taking second derivatives sometimes it becomes a problem, and then being able to solve is not always possible, even for polynomials. Yeah, sure, in here we're going to be able to solve for the first derivative and then second derivative and see what the roots are, okay? So where there's 0, that won't be a problem. But if you go, in your polynomials to the degree of 4, and then to 5 and to 6, you're probably going to be using some kind of a tool to find your roots. And that's okay, but if your teachers don't allow you to do that, and you maybe don't have a calculator that does the roots for you, okay, then you're going to be a little bit stuck. But the concept still applies, right? So concave up still means concave up. It's related. to your second derivative being greater than 0. Concave down, okay, is again related to your second derivative, okay, and that is your second derivative is less than 0, so that's concave down. And then when your second derivative is equal to 0 at a point, then we have to check what's happening in the vicinity to be able to see if it's an inflection point, which is a change of concave up to concave down or vice versa, or if it's an actual possible maximum or minimum at that point. All right, so for this example, I will take, so this is a very well-behaved function, so I'm going to take first derivative is equal to, so it's going to be 3x squared minus 6x plus 1. And then my second derivative here is equal to, I guess, 6x. And this is going to be minus 6. So the second derivative is going to be easy to solve to see where it is equal to 0. And now we want to be able to see where this function is concave up and concave down. And then we can do much more as well. So first, let's concentrate, okay, and try to find out, okay, what's happening to this, okay, in terms of concave up and concave down. So if I solve this, and if I set this equal to 0, well, then that's not very difficult. I'm going to get x is equal to, if I bring this over to the other side, divide by 6, I'm going to get this 1. So that means that my second derivative here is equal to 0. And now, how do you check if it's concave up and concave down? Well, so what I'm going to do is I'm going to say, all right, so let's make this x is equal to 0 here, and then x is equal to 1 over here. So I know that at this point, this function, so something happens here. I don't know if it's concave up, concave down. Okay, at this point, this is actually 0. But to the left of it, I can certainly find out what happens right here. So to the left, I'm going to keep this orange. Now, you can take a test point. So I'll take the test point 0, substitute it into my second derivative. So 0 times 6, and so it's going to be negative. So on this range, my second derivative is less than 0. What does that mean? This is concave down. That's what that means. Now, if you take, for instance, on the right, okay, of right here, so if I substitute in here, I can take a point, for instance, 2. So I'll substitute 2 into here. So I'm going to get 2 times 6, so 12 minus this 6. This is positive. So notice that right here, what I have, so this is f, second derivative. Here on this side is actually greater than 0. And maybe, I'll put the color as well, okay, within here so that it matches. So that means that this in here is concave up. So what happens in here? What is that telling us about this point right here? This is an inflection point because it goes from concave down to concave up. So that I know. And this function, so concave, down, so that means the function's kind of going like this, okay? And then it turns up, right? And it happens at x is equal to 1. Now, we can take this even further, and we can go back to see, so right here, so we will be able to go back in here to our first derivative if we wanted to see if there are maybe any possible maximum and minimums in here. So I'm going to set this to 0, and I'm going to find the roots there. So I'm going to do that in fast-forward fashion. This is just a quadratic. And then we're going to be able to see, I'm going to test if it's a local maximum or local minimum. And then I'm going to plot it for you just so that you can see exactly and tie it into, concave up, concave down, this inflection point, you know, how it changes there at particular point x is equal to 1, and then see the maximum and minimums. Okay, so let me do this in fast forward fashion. All right, so here are the, you know, the roots right here. So they're not the prettiest of roots. That's fine. And now what we would want to be able to do is, so we know that the tangent at those particular 2 points, so it looks like it is somewhere, so this is going to be somewhere 0.18, so it's going to be somewhere over here, and then 1.816, so it's going to be somewhere over here. All right. So at those 2 particular points, notice that this point lies on the left where the second derivative is less than 0. So what will that tell us? So if it's less than 0, then it's concave down. So that means at that point, it is some kind, so concave down, so it's some kind of a local maximum, right? And then over here, okay, so notice at this point right here, okay, if we would substitute it into here, which we can, into our second derivative, I've already done it because I've shown you right here, so that means it's concave up. So that means that this is going to be some kind of a local maximum. So that's what this will look like. Now, if we combine all of this together, you know, I can kind of sketch this function because I have an inflection point from down to up, and that happens at 1. So what my, you know, visualization is going to be, okay, kind of like this. So this is going to look most likely, so something like that. Now I should probably, you know, clean this up a little bit, make it a touch nicer. So my guess is this. Okay, so this is what's going to happen. Here's your inflection point. This is at x is equal to 1. Here is your local maximums and minimums, and then because this is a cubic, right? So notice it's a cubic function, and it's positive here. So that means this is going to blow up in this way, and this is going to blow up in that way. That's how that function is going to look like, and I even know where all these points are. Okay? So let me graph it just to try to prove it to you. All right? So let's take out Desmos in here. I'm going to punch this function in here. So this is f x equal to, and this is going to be x cubed minus 3x squared plus x plus 1. There we go. Okay, so that's exactly what happens. It's kind of how I drew it right there. And notice, so this is your point. So that's your first one, 0.18 decimals is rounding this, right? So you have those roots in there, and then here's your other one, you know, 1.816. So everything aligns. Those are your local maximum minimums. And here is your inflection point. All right, so here's your inflection point that you are able to see. Okay, so what actually happens there. So that's pretty cool. And you know, the concave up and concave down, we can clearly see that it's concave down, okay, on the left of x is equal to 1. So it's concave down. And then it's concave up to the right of it. And then it looks like it changes there at that particular point. So very neat to be able to see that. Here's the second example. So this one is not as easy because it's of degree number 4, right? It's still a polynomial, so it's still pretty nice. Now, sometimes you get functions which may not be as nice, and then you're really stuck and you kind of have to use visual tools and graphing tools. So from calculators or applications, anything bigger, it makes no sense really to do it by hand, right? Unless your teachers kind of want to torture you or they give you some additional information. So for this one, I am going to give you an additional piece of information just so that you're not struggling all the way through. And that is that the first derivative is equal to 0 at 0.5. So that means you will know one of the factors, right? Or one of the roots, okay, for your first derivative. So let's do this. So first off, so this is going to be g. Okay, I'm going to find the first derivative. So this is 4x to the 3 plus 6x squared minus, this is going to be 2x minus 1. So that's my first derivative. And my second derivative, so right here, is going to be, so again, so not very pretty. So this is what I have, plus 12x minus 2. Okay. So unlike the first example I showed you, now if we want to find concave up and concave down, okay, now we have to solve a quadratic, right, to find the roots. Where does it equal to 0? No problem, okay? So let me do that in fast forward fashion. So let me just find those two particular points by using the quadratic formula. All right, so there you have it, okay? So this is where the second derivative is equal to 0. So now we don't know if these are going to be inflection points or not. Let's take a look, all right? So let's see what actually happens here. So again, you know, I always like, I mean, sometimes you might see it in textbooks or teachers will use a table. I like to actually visualize it as a line, you know, and then see. So I'll, you know, put 0 here. So this is my x. And then I will input. So here, you know, I have negative 1.145, etc. So that's one inflection point. And then to the right of 0, you know, 0.145, you know, etc. So at these 2 points, my second derivative is equal to 0. So now I want to be able to see what happens to the left over here. So I can substitute, for instance, negative 2 into my function. So if I substitute, okay, negative 2 into here, what will I get? Is it going to be positive or is it going to be negative? Okay, so let me substitute it and just check. All right, so it looks like the second derivative there is positive. So let's see what happens, you know, on this. Okay, so to the right, but just before here. So is this positive or is it negative? So positive means it's concave up. And now in between here, let's see if it's going to be concave up or concave down. All right, so for here, I am going to choose 0 because it's the nicest number to pick. So 0, so it's going to be negative 2, which means this is going to be negative. All right, so right here, it is negative. So that's what I have in here. So that means this is an inflection point. All right, so it's changing from up to down. So possibly, you know, something that's going up and then it's going to start going down. Now so again, so to the right, so let's say right here, let's see what happens at this point. So I can substitute 1. So I'm going to substitute 1 in here. So that's going to be, it's definitely positive. So right here, so this looks like it's positive. So notice it's going from negative to positive. So another inflection point there. All right, so for this example, we have 2 inflection points, you know, so we have kind of change from concave up, so something up, okay, something down, and then I guess it's going back up again. So, you know, my guess, because it's to the 4, is it positive? Yeah, it's positive. My guess is that this function looks, you know, something like this. It's kind of blows up. Okay, it's going to have some, so this is going to be one of your first inflection points here. It's going to change back up. Here's your second inflection point, and then probably looks like this. Okay, so that would have been this point. This would have been at that point. And then it looks like it has, you know, my guess is that it would have 3 places where we have a local maximum or minimums. And in this case, okay, you know, it's, you know, so it's right here. Now, it may not be symmetric, right? So, you know, it may look something like this, like it may be like that, right? Doesn't mean that these two are going to line up. I don't know that. I would need to know a little bit more information and I would have to plug it all in. I'm just kind of sketching it out. But I do know that I have my 2 inflection points somewhere in there. Okay, so If I wanted to know those, okay, so if I wanted to know these values, I would actually have to solve this. So I would have to solve this entire thing right here for and set it equal to 0. Now I know it looks like, so I have one of these points given to me. So that's going to be at 0.5. So at 0.5, so it's somewhere over here, right? So it's somewhere over here. So it looks like it's the last one. So it's concave up at that point. So this concave up, so this is definitely at that point. So that means I'm trying to find these two other roots. Now, how would I do that? Well, okay, if you're stuck with something like this, how would you do that? So let me just highlight it in here. Let me copy it. Set it back down here. If you can't use online tools where you're finding what the roots of this is, so to factor this whole thing out, ooh, that's mean. But you do know that one of the derivatives, this is 0.5, this is equal to 0. So that means you can factor this out. So because I know this, so that means one of the factors is 0.5. So what I would do is I would do the following. So now 0.5, I guess you can do it in one of two ways. So here is 1, and now I'm going to have to factor this whole thing out into this, right? So now I don't know what this is, but I do know that it's going to be a quadratic, so I would have to do long division here. Okay, now this is one of the roots. Now obviously if you solve this, 2x minus 1 equals to 0, you're going to get 0.5. That's how I got that, okay, within here. But now the rest, I have to actually do long division. So I would have to do all of this mess. So 2x minus 1, and then I have to do it, okay, and then factor this whole thing, x squared minus 2x minus 1, okay, and then do the whole procedure to get my quadratic in here. Now that long division, if you forgot it, okay, I'm going to just put up a link up above there. That dates you back to probably grade 11. I don't think it was in grade 10. I think it was in grade 11 that you have there. So factoring out kind of longer polynomials. I'm going to do this in fast forward fashion. I'll find the quadratic and then I'll find the roots. And you can test yourself if you like. Okay, I'm going to just do that in fast forward fashion. I'll be back. All right, okay, so here it is. It's not terrible, okay? So here's the factoring out, okay? So doing that long division in terms of that. So now I have my quadratic, and now I'm going to use the quadratic formula to find my roots, okay? Be back. All right, so here you go. So here are the roots. And now, so if you take a look, so negative 1.70, etc. So, because we already did the concavity. So that would be negative 1 point, sorry, was it 7? 7, so that's a little bit further. So that's going to be here. So it's concave up. So that's this one right here. So that is going to be a minimum there. And I guess the other one is right here. So that's going to be this one. So this one is going to be a maximum. All right, so we've used all of these wonderful now tools to be able to find these things out. Let me just for completeness, I'll plot it up on Desmo so that you can see the function, and let's see how good we were. Well, there it is, okay? So, yeah, it looks correct. Yeah, so it looks correct, or did I mess this up somehow? It was negative 1.707. Yeah, so that's fine, negative 0.29. So that's correct, and then this one was given to us. That's the 0.5. So all of those, so notice the maximum and minimums by concave up and concave down by the second derivative. So that all works. And then we have inflection points. And those inflection points happen at -1 point. So I guess somewhere -1.14. So a little bit further somewhere here. I guess it starts to change there. And then the other inflection point was at 0.145. And it does indeed make sense, because notice that it's concave down and then concave up. And then on the left-hand side, it goes in concave up, and then it starts to switch back up. So, and even the plot, so notice my original thought was that it might look like this, which was very symmetrical, but clearly it actually looks kind of like this. Right, where it's not as symmetrical, but we can tell what that is, and we can find those. What the beauty is now we can do that, because once we now have all of these, and I'll do that in a future video until like full out how to sketch without using decimals at all, because now once we have these points, we can just start substituting. We know where the inflection points are, we know what the values, we can substitute it back to the original equations or function, and then we will know exactly what's happening. All right, super long video for this, but I think these concave up and concave down are really neat and definitely worth your time. You will run into problems if the functions are going to be sometimes rational, very long, complicated. With polynomials, it kind of works out, which is probably what you're going to be doing in your kind of grade 12 calculus in the beginning, or maybe first year even. But if anything further, you're going to be using tools, right? You're going to be using graphing tools, but the concepts you should understand, because now you can do maximization, minimization problems, optimization problems by using concave up, concave down to check if it's a max or if it's a min. Thanks for watching. We'll see you in a future video. Bye, everybody.